In the first two videos of this series, we have performed a complete residual strength analysis and crack growth analysis of a stiffened panel. All that we have determined the inspection period for that panel. What I want to do in this third video is to explore a little bit the capabilities of XTTD regarding analyzing design alternatives. Okay, so I will start here by opening the same configuration file that we used for the initial analysis, and I will generate a design alternative here. So let's say I think this frame 15 is too heavy. I want a lighter frame. So I come here to the database and I will select, instead of frame 15, which has 400 millimeters of area, frame 13, which is a bit lighter. So I just load this, confirm, and I will generate the panel with exactly the same information I had before. So the only change, I don't want to save this, so the only change is the cross-section of the crack arresting stiffeners. So I will now run the analysis again, exactly the same way I did before. So I will run a crack growth analysis with 20 increments of crack growth and having the crack growing to 270 millimeters. It should take around the same time, around 40 seconds. It took a bit less. And let's now look what that design change has made to the residual strength diagram. And when we look at this, we see some things which can be counterintuitive. For example, if you remember the first analysis, the critical crack length was 128 millimeters. And now we get almost 141 millimeters here. But why is that if the stiffeners are lighter? Shouldn't that decrease the residual strength and later the crack growth, the inspection period? The thing is, because the central stiffener is broken here, and the original hypothesis is that without a crack, the sheet and the stiffeners, they have the same strengths. When you use a lighter stiffener, the result is that the load that is thrown by the broken stiffener into the sheet is less, the lighter the stiffener is relative to the sheet, right? And that is why, because the load in the end is lower, I have a larger critical crack length here. And we can see that even with the lighter stiffener, the structure is still damage tolerant because the crack recovers. Its residual strength go above the minimum. And we see that the further mode is the same. The attachment line is failing, but it's failing at a larger size. In the previous design alternative, it was 250 millimeters, now 256. Not very big changes, but they seem a little bit counterintuitive. So it seems that using a lighter stiffener is better for this panel, okay? So I will leave this as design alternative 2, so we can later compare with design alternative 1. So with this new 130 millimeters critical crack length, I will now run again the crack growth analysis. Right, so I will open the same panel we used for the crack growth analysis, and I will make the same change here. So I will change the stiffener cross-section to stiffener cross-section 13. So this, I don't want to create the panel, not save, and I will run the analysis again. Again, elastic behavior is fine, 50 increments of crack growth, and now 130 millimeters of critical crack length. And we run it again. It will take around 12 seconds as before. And let's look now at what is happening with the crack growth cycles here. And we can see that despite the crack growing to a larger size, the number of cycles has not changed very much. Let's look at this in a better way. So I will save this again as design alternative 2, this panel, right? And now what I will do is that I will open design alternative 1 here, so that we have both open. And next, you can always do that. You can open as many case studies or design alternatives as you want. I'll just change this name here. So yeah, design alternative 2, so that we can have a better comparison name in the labels. For design alternative 2, we have this crack growth diagram here. Let's get the same diagram for design alternative 1. Okay, so here we then have the diagrams for both panels. Something that I want to show you is that for everything that we do with XDTD, immediately we can calculate the cost and weight of the panel. This is done by taking the properties that are in the database and using the geometry to calculate the cost, and then using a factor that is in the database for each type of material, for stiffeners, for attachments, for sheet, which I defined here as I wished, but for every institutional company, the values can be used to reflect their actual costs for each type of component. But the fact is, for every structure or case study, I can immediately have what is the total weight, how the weight is distributed to sheet, stiffeners, and fasteners, and the same distribution in terms of percentages, and the same information for the cost. Obviously here, the stiffeners weigh less than the sheet, but because of the parameters I use, the stiffeners cost more than the sheet. But then again, that is as good as the information in the database, which depends on the information each institution or company has. But what I really want to show you here is that with XDTD, I will clear this because I don't need it. So I have the two panels here, and I have performed the analysis. There are two things that I can do that are very helpful in the design. First, I can compare results. So I will, in this case, compare for both analysis for the crack tip. For crack tips, I will compare the crack growth cycles. I will choose just one of the crack tips because it's symmetrical, and I will do that for all of the case studies. In this way, I can have any result compared. And we can see that we have the comparison here. Design alternative 1 is in green, design alternative 2 in blue. And obviously here we see that the crack grows to different sizes here, and the difference in number of cycles can be seen here. We actually can look at this if we don't want to make out. We have this data here, which will compare the two trusses, which are the two curves, and plot what is the difference in the number of cycles here as the crack growth. So in the final stage, we can see that we have a delta of 243 cycles. Okay, so as we could see here, the number of cycles is not very different, which means I can use a lighter stiffener and get away with it, right? Because the lighter stiffener gives me a damage tolerant structure as required, and the number of cycles is not very different. It's actually a bit higher. But then what could be the decisive factor for the choice? I can compare weight and cost. So let's compare weight and cost of the two solutions here side by side, so that we can see that for the design alternative 2, we have here a total of approximately 15.9 kilos. For alternative 1, 16.4 kilos. And for the cost, actually a bigger difference, because for the cost got simplified because the stiffener, which is the variable we changed here, it has a higher cost, right? But what I want to show you here is that it's very easy in XDTD to change design variables, run the complete analysis again because it runs very fast. It offers lots of facilities to compare results, to understand what is going on with each result, and to analyze the merits, both in terms of the result of the structural performance I'm looking for, but also as the cost and weight of each solution. So, and I think this is very important because I've seen cases where most of the analysis to determine inspection periods were performed too late to be able to change design variables. So in order to have the inspection period as a very important design variable, it is necessary to be capable of doing this analysis in very early design stages. And for that, you need a simple model. Obviously, for certification later on, you need to use 3D models to compare with test cases. But for the initial stages, a 2D analysis of this type is perfectly fine. And it allows to compare the merits of different design solutions. I changed the cross-section of the stiffener. I could change the spacing between the stiffener just at the click of a variable. I could change the rivet type, the pitch. So most or all of the design variables, I could change materials, everything, but can be done with exactly the same facility that we have done here. And important to note as well that although the difference in weight and cost can look small here, we have to remember that normally we are just this panel that we are analyzing is repeated in lots in the complete structure. For example, if this is a fuselage panel, I'm just choosing a representative area, but the geometry, materials, and stiffener will probably repeat. So the difference is actually much larger than is shown in this analysis here. So with this, I conclude this third video of the series, and I hope it has helped showing how XDTD can support a better design aiming at a better inspection period for damage tolerant structures. Thanks for watching.